Hello and welcome. From Belgium to Brazil, Portugal to Puerto Rico, engineers from over 16 countries around the world have joined us today for the latest edition of the Wednesday webinar series hosted by the Concrete Preservation Alliance. My name is Chris Ball. I'm with Vector Corrosion Technologies, and it's my pleasure to introduce today's program and our featured speaker, Dr. George Sergi. The Wednesday webinar program is a series of monthly educational webinars from August 2020 to July 2021, addressing the best practices and new innovations in the field of bridge preservation. Future webinar topics include galvanic encasements for severely corroded structures, impressed current cathodic protection, non-destructive testing, post-tension evaluation, and post-tension tendon impregnation. Before we start, I'd like to remind you that this is a live webinar and it is being recorded. The Concrete Preservation Alliance is a coalition of organizations that are committed to advancing the best practices of concrete preservation and infrastructural renewal. Together, we work together to promote education and awareness, new innovation technologies, and sustainable concrete practices. The Concrete Preservation Alliance hosts a website called WeSaveStructures.info. It's an educational website which promotes good concrete repair practices. The members of the Concrete Preservation Alliance are Vector Corrosion Technologies, NDT Corporation, Vector Corrosion Services, and Vector Construction. With regard to sustainability, did you know that approximately 40% of the solid waste comes from construction and demolition? So the construction industry is a rather large user of natural resources and raw materials. So making structures last longer and reusing existing structures compared to the cost of demolition and rebuilding provides not only economic benefits, but also reduces the consumption of natural resources, the production of pollution, and construction waste. On the WeSaveStructures.info website, there is an environmental calculator that's free to use. It's basically you input the volume of concrete that's going to be repaired and maintained in place, and it'll calculate how much natural resource consumption is avoided, the avoidance of pollution and waste generation from demolition activities. So please take a moment to stop by WeSaveStructures.info to see our environmental calculator. Also on the WeSaveStructures.info site, you will see this is the site where you registered for today's seminar. Under the events page, you see the upcoming events for the Bridge Preservation webinar series. The current presentation today is by George Sergi. The upcoming presentation in October is by yours truly. Please stop back regularly to see the upcoming events, and as well to get a copy of today's presentation and the video recording when it's available. Now on to our speaker, Dr. George Sergi. We're very honored to have him here today. He is the Technical Director for Vector Corrosion Technologies in the Birmingham, UK area. He leads the research and development group. He was a PhD in corrosion of steel and concrete from Aston University. And while he was at Aston, he led the team that developed the original embedded galvanic anode for concrete repair. He later became the head of corrosion at the BRE in the UK and technical manager at Fosroc International. As you may know, Dr. Sergi has published his work extensively and is co-author or author of numerous publications and owns several international patents, and is taught at many universities around the world. Today's presentation is on corrosion protection and extending the life of concrete repairs for bridges. The learning objectives today, George will cover the development and the 20-year performance history of embedded galvanic anodes for concrete repair, and also discuss applications for embedded galvanic anodes including concrete repair, joint repair, and bridge widening. And you see there on the picture on the right, there's George. He actually does leave the lab periodically. He's on a construction site in Italy in his high-vis jacket. So without further ado, we'll turn it over to George for today's program. Thank you.
Yeah, thank you very much, Chris, for the introduction. I'll move on from this slide. I don't want to be looking at myself. I think where I start really is go back in history and talk about how the idea of a galvanic anode came about. This was when I was in the mid-90s, early 90s at Aston University. Fosroc came to us with a real problem that they had, which was when they were repairing or at least selling repair materials, the complaint that was coming back was that there was corrosion occurring around the periphery of the repair. And they asked us to investigate this and see if we could come up with the solution to the problem. And as you can see here, this is a sort of an original repair, but within 2 or 3 years, it started having corrosion just on the edge of the repair. And what you end up doing if you're not careful is sort of chasing up your repairs. You're repairing one area, it then forces corrosion to occur in adjacent areas, and then you go and repair those and so on, and you're just chasing your repairs. So we had to come up with a solution. We identified this problem as the incipient anode formation. Essentially how it works is if you have a patch repair where you're producing a very nice cathode, as we call it. Now I have to explain what a cathode and an anode is for those who are not familiar. The anode is where corrosion is taking place, where you've got your dissolution of your iron, and your cathode is what drives the anode. So it produces the electrons that move across, and the consumption of oxygen and water does that, produces hydroxyl ions, which actually is a positive thing for us. And I'll talk about that a little bit further later down the talk. So as soon as you apply new fresh concrete onto your steel reinforcement, it's nice and clean, it immediately wants to be the cathode. But if it's a cathode, there has to be an anode as well, and the anode tends to occur on the outside of the patch repair, where you probably still have a little bit of contamination of chlorides, and therefore the potential would sort of take a more negative value compared to what's inside the patch repair. And that obviously is a driving force for the electrons to move across, and you set up this battery, if you like, anode, cathode, and the corrosion initiates pretty quickly outside the patch repair. And in order to try and avoid this process, we thought, well, if you can put a galvanic anode inside the patch repair itself, it then becomes, it maintains the anode within this patch repairs. So this now is the anode, and that is corroding preferentially to all the steel around it. Even though this is minus 350, for example, this is a lot more negative, so that immediately becomes the anode, the corrosion site. So the zinc is sacrificially corroding to protect the surrounding area. So the purpose originally was to prevent corrosion from initiating in a chloride contaminated environment, primarily outside around the patch repair, as we were understood at the time. Looking at sort of standards that were available, the only thing that we could find for preventing corrosion was the EN 12696, ISO 12696, where it states that to have an effective cathodic prevention current, you need to be in the range between 0.2 and 2 milliamps per meter squared. There was no other criteria, for example, about shifting of potential. So this was basically the standard that we were looking at. Now, obviously, zinc going straight into concrete it really doesn't work very well. It passivates quite quickly. Concrete has a pH of around 13 or so, and at that level, the corrosion rate of zinc is not very high. It corrodes initially and then it passivates. So we needed to find a way of keeping it active and making sure that the zinc was corroding. So we moved across to increase the pH into very high levels of over 14, which maintained the corrosion, the activity of the zinc continuously. And the way that we did that was actually to use saturated lithium hydroxide. Lithium hydroxide has a pH, or saturated lithium hydroxide has a pH of 14.6, and being saturated means it maintains that pH for as long as saturation exists. So that was our starting point. Lithium hydroxide is the activator, encased in encasing mortar, but we also made sure that the mortar itself was highly porous, so that it can contain the corrosion products that were coming out of the zinc and the zinc metal. After a few trials in the lab, we went out to do a trial, a field trial, an actual structure, a bridge in Leicester in the UK, and this was in 1999. But before I go there, I just mentioned that the type of anodes that actually exist and which one we were concentrating on at the time. There's a type A anode, which is alkali-activated. This is the one I'm talking about, and that was the prototype that I just explained. There's also a halide-activated zinc core that would normally be chloride or bromide. Although we provide, as a company, we provide both of those, but we normally use the alkali-activated because it has a better performance, and we know a lot more about it as well. So there's a type 1 that's installed in standard repairs, and then there's a type 2 which is installed in sound concrete. Though I will show those examples later on, but let's now concentrate on the on the trial. This is what it looks like. Basically, it's the A50. Carries a fair bit of traffic, and this is the deck at the top. This is what's supporting the deck. It's the cross beam sitting on columns. We identified a couple of areas there which we could monitor. The whole structure was actually was repaired in the same way, so we had a load of patch repairs all around. Each one of them had galvanic anodes inserted, but those were just connected directly to the steel reinforcement with these tire wires that you can see here. In this case, because we wanted to monitor it, we cut off the tire wires apart from one. We attached a lead to that and took it out into a junction box, and from the junction box we then connected to the steel reinforcement at several places so that to ensure continuity. And all we had to do then was carry out the repair and then monitor the performance of the anodes. These are the anodes that are laid out. There's two adjacent areas. One contains 8 anodes, the other 4 anodes, and the spacing is about 600 millimeters. We didn't know any better at the time. We just thought, well, let's start at this. Looking at the potential map of the structure beforehand, the area that we repaired, we could see that there was a high corrosion area, and it coincided with a high chloride concentration. As you can see here, we got as much as 2% chloride in the corroding areas, but even as you know, in other parts of the same structure, we'll be getting chlorides which were more than 1%. So 2% is considered to be extremely high. It's greater than 1.5%, and therefore it obviously needed to be replaced. So we took out all that that concrete, but there was no attempt really to remove all the chloride contaminated concrete, and that's what you would normally expect. We just took it out to clean steel and embedded the anodes. Okay, so one of the things we monitored using the junction box that we had was to monitor the current output of each individual anode. And these are all the 12 anodes that you can see here. You can see that the current is gradually decreasing with time. Most of them are within reason, quite similar, apart from this one anode. And at 10 years, we were able to take out an anode from an adjacent patch repair, not the actual monitored area, but one close by, which was set at the same time. So we thought the same thing would have happened to that. And we analyzed, we took it apart basically, had a look at it. We could see that that was the original zinc core. It's now covered in corrosion products, which if they're removed, you can see that there's still zinc underneath. The scraping of that, you can see that this bright zinc still underneath. There's no signs of distress at the interface. There was no cracking or anything, but we could see a lighter face down here, which when we looked at closely, we could see as a cross section here under a special light. This area was actually filled up, or the pores were filled up with corrosion products, zinc oxide corrosion product. So it now looks quite clear really how the process was happening. The zinc was corroding. The empty space that was left behind was filled with the corrosion products, and the remainder of the corrosion products migrated into the mortar, which was porous. Okay. At 20 years we did the same thing, obviously. 10 more years later down the line, and you can see that there's quite a chunk of corrosion product on the surface of the anode. We then removed the anode, the corrosion products, and had the bare metal left behind. And you can see that it's still pretty intact, really, within reason. There's obviously we've lost a lot of zinc, but it's still there, and it can continue to produce current. What we actually found from that, if I can just go back to that slide again, by taking over the corrosion products and measure and weighing the anode, we could find an efficiency of how well the anode was actually performing. And the way that we did that was to because we're monitoring the current with time of all individual anodes, we knew what the current delivery was from this particular one. We converted that to charge, and using Faraday's law, we calculated a mass loss, amount of zinc that we actually lost, and compared that to the actual weight, and that gave us an efficiency which was at least 70%. This is all the anodes, mass loss by calculation using the efficiency of 70%. And we can see that on average we still have about 40% of the zinc remaining. Okay, one of the other measurements that we were taking was to measure the potential of the steel, both during when the anode was connected, when it was disconnected as the instant off, but also 24 hours later. We call that the depolarized potential. You can then determine the depolarization potential between time 0 and time 24 hours. But we were very interested in the depolarized potential, which we took to be roughly the rest potential of the steel at that point. And we could see that with time that potential was rising. It became less and less negative, and we've reached potentials which are believed to be passive, i.e. the steel is no longer corroding when you have potentials less negative than minus 200. The next thing that we did was to convert the current density into a charge delivered by the anode, and then use the accumulated charge. So charge is basically the current in amps times the time in seconds, and that's coulombs. Here we plotted kilocoulombs, so it's thousands of the coulombs with time. And then we assumed that the initial current was 250 microns per anode, and modeled what the shape of that cumulative current will be if all we were taking into account was the reduction in the surface area of the zinc. So as the zinc is being consumed, it's getting smaller and smaller, and therefore the current that will be delivered, which will be proportional to that surface area, will be reducing proportionally. And although that line looks almost linear, it's actually curling over, and eventually it'll just stabilize when the zinc is completely used up. So for the first 6 years, we were seeing that actually it was bang on. The assumed current density that should have been delivered by the anode was actually being delivered. We then had a little bit of a diversion from that line, but then it followed a second line consistent with 100 micron current density, current output. And then there was a third deviation, or rather a second deviation, where the current output diminished to something like 60 microns. Obviously, something would have caused these to happen. We are pretty certain that we know what happened at this stage, and that's because we were adding lithium hydroxide just enough for a 10-year life of the anode. That was the original design. Okay, it lasted a bit longer, but eventually it was going to run out. So here we've now got non-saturated lithium hydroxide, i.e. the pH is beginning to drop, and we've, as I've shown earlier, activity of the zinc depends on the pH of the electrolyte. So we measured the pH from the anodes that we removed in the for electrolyte, and that was pH 13.9, so it dropped from 14.6. Therefore, that reduction in current output was related to that the consumption of the lithium hydroxide. So what caused that? And the speculation, as far as I'm concerned, I think it's probably correct, but we're sort of checking that out, is that the corrosion products became so numerous and they were starting to block the pores sufficiently to restrict the current from flowing freely. So there was a sudden critical concentration of corrosion product, which reduced the porosity significantly and started to slow down the current density. So that's what that one is. So we get a profile which looks like that. Considering that we were working on a 10-year service life, I think we pretty much got it right in terms of predictive current output. The only thing we have to deal with is this little hump here, and we think that we pretty much dealt with that quite well in newer anodes, because what we've done, we've increased the lithium hydroxide concentration up to about 7 times from that initial one. By doing that, lithium hydroxide is obviously soluble, it's being consumed, and that whenever that is being consumed, you open up pores, so there's a lot more porosity available for the corrosion products to replace and get into. So that will most likely be delayed, although we haven't got any data to prove it just yet. That's likely to be the case, and that obviously we've dealt with that one by adding additional lithium hydroxide. So hopefully our profiles will follow that green line for much longer. One other thing that we were measuring, which turned out to be quite a useful parameter, was what we call the instant on current. So when we finished with our depolarization at 24 hours and the anodes were off, when we turned them back on, we measured the current output within 5 seconds of turning them back on. And we call that the instant on, and that represents the power of the anode at that particular time. So, you know, how much current is capable of producing when you first switch it on. We could see that we could get more than 1 milliamp per anode for most of its life, but at around 14 years, which is at the time when we think that the lithium hydroxide was consumed, or at least went to non-saturation conditions, that current output had diminished considerably. So this gives us a sort of a profile of how the anode power lasted over the years. Okay, so again, going back at the 20-year results, we did a potential map. We did that every time we actually took some measurements. We did a potential map of the whole area. And at 20 years, we could see that there was an area where corrosion might have been occurring. You can see that within the patch repairs themselves, the potentials are very, very noble. There's obviously no corrosion there. There's not very much corrosion. Again, the potentials are noble, and the steel is passive. But there's a question mark around this area here between the two adjacent repairs. And actually looking at it, after 15 years, although to be honest, I hadn't noticed it at the time, but I was taking regular pictures and looked at them later on, and I found that there's a hairline crack in the 15-year photograph. It's just beginning to, which coincides with the time when our current density had dropped. So maybe corrosion area was beginning to happen here. We were no longer able to prevent corrosion from happening. That hairline crack grew into a larger crack, a continuous crack that then eventually got into the patch repair itself. This is the one patch repair. The other one is down here somewhere. So in between the two, which is away from the anodes, the anode will probably be the nearest one, will probably be down here, and that's, I would say, 300 at least millimeters away. So it's lost enough power not to be able to protect that region. So looking at the current output over time, if you plot it on a logarithmic scale, this is the average, the mean current density of all the anodes. So it's current density by steel reinforcement. We can loosely put a straight line through it, and the fact that it's a straight line on a logarithmic scale tells us that the current is actually halving every frequent time scale. In this particular case, it's every 7 years. So if that's your initial current, at 7 years, it's half that. Another 7 years, at 14, it's half again. And at 21 years, it's halved again. So it gave us an understanding of the performance of the anode set. We know how long it can last, and we know how the current is diminishing with time. Another thing that we noticed, obviously, is that beyond the 14 years, which was the time when the patch repair was working well, and then we had the initiation of cracking, the current had dropped significantly at a value lower than 0.4 milliamps per meter squared. Now the standards still say that your current density can be between 0.2 and 2 milliamps per meter squared, and although we're within that range, obviously we weren't protecting the steel reinforcement adequately at that situation. Now, there's a couple of things that I could say about that. One is that the team that suggested this 2 to 2 milliamps, Pediferi's team in Italy, later explained that in fact the newer results were showing that you probably need 0.4 milliamps per meter squared as your minimum. But also, when we're measuring the current density, we're taking a mean current density over the whole surface area, and between the anodes, that it's likely to be probably half of what you're assuming to be the average. So even though we may be measuring 0.4, it probably is 0.2. So I put a new line there suggesting that we probably need to be above 0.4 in all our future designs. But nonetheless, up to 10 years, which was our design life, we got no corrosion. So we're happy that what we designed was actually, it worked, it served its purpose. Okay, so we learned quite a lot of things just by looking at that, and in fact some other results. This is not the only one that we monitored. We've got maybe 20 or so monitored sites. A lot of them have gone beyond 15 years now, so we have a lot of data. And just looking at all that data, obviously we managed to get an empirical determination of the current output per anode type. So different anode types will give you different current levels. We can determine an aging factor, which is related to half-life, the half-life principle. So every so many years, so your aging factor could be 7 years, could be 10 years, could be 12 years. I'll show you later a table that we analyzed all of that. So we've now worked out how the current density diminishes with time. There was a reassessment, obviously, of the lithium hydroxide content, and like I said before, we've increased it in certain anodes up to 7 times as much lithium hydroxide. We also redesigned the connecting wires. There's 2 reasons for that. The main reason was that it became easier for installing purposes to have a single wire going through rather than 2 sets of wires. It's a lot shorter in reality to install one with just the 2 wires. But there was also a slight problem we occasionally saw where the 2 wires were touching each other in the zinc core. There was a sort of an interstitial gap, if you like, and some lithium hydroxide solution could penetrate through that gap and start corroding the zinc from the inside. And it's now, there's no way that can happen now because it's a single wire and it's totally encased in the zinc metal. And we reassessed the current density requirements. The standard, we assume from the standard that you need a current density of 0.2 to 2 milliamps per meter squared if you're trying to prevent corrosion. I'm now saying maybe we need 0.4, and maybe the standards should be updated to that. And from everything that we learned, we can now have improved specifications and a more intelligent design parameters. We can design in a better way, having better knowledge of how our anodes are actually working. Okay, so over this 20-year period, we went from this very simple hog-shaped anode, which was a copy basically of the prototype of the ones that we were using in the lab to develop the anode. It was easy enough to cast in a little pot, so that's why it got that shape. But now, obviously, understanding better and knowing that we need improved surface area, but bearing in mind that we got to keep the mass up as well, we've redesigned a range of anodes. Obviously, easier to install because that would give you, it will make it very stable against the steel reinforcement. And like I said, there's an increased amount of lithium hydroxide to take into account the longer life that we are able to achieve. And for cases where there may be drying of the concrete and the anodes are at risk of drying, particularly when they're being placed too close to the surface, we developed what we call a 2G generation, where we've included a non-corrosive humectant to maintain a high moisture level in the anode itself. This is what actually replaced the XP anode, the prototype that I've been talking about most of the time. So the XPT, this is called now, that's replaced the XP. We have a 2 times larger surface area anode, which we call XP2, and a 4 times larger anode, which is called XP4. So the current output increases as we increase the surface area, and we were able to see that in some of our early studies when we were first making the anode. And you can see the current from the lowest surface area, it then doubles and then it's 4 times higher. All of these were encased in a single slab facing the same steel reinforcement. So when they all had to work in the same way, we have these current that obviously was related to the surface area of the zinc. Okay, so I'll talk a little bit about applications now. I talked a lot about incipient anode formation, and this is what we were faced with, obviously, when we're talking about patch repairs. This is a parking garage, and to carry out the repairs, if you attach your galvanic anodes around the periphery, like that, then you are protecting the adjacent area. So you're avoiding those incipient anode forming and breaking your concrete. But it can work just as well anywhere where you have new concrete being cast against an old concrete. So in this case, there was a bridge expanding, widening. You have the original road on this side, and you're adding a lane. In this case, you're connecting the steel reinforcement to the old steel reinforcement, and you have old concrete, and you're going to place new concrete, of course, on the new construction. That is a susceptible area because it's likely to be, even if it's only low contamination, the pH will be lower. So immediately when you connect the two together, this is going to take the form of the anode, and this new patch is going to drive the anode and drive the corrosion. So installing anodes along the edge of this joint would stop this incipient anode formation. Same again when you expanding your structure, you have an original concrete slab, and then now you're trying to build on top of it. So again, at where the old meets the new, it's good to have a layer of or a line of anodes that will protect your old structure from corroding. One of probably the biggest, or I think it probably is the biggest repair project in the UK was a 2-mile section of a viaduct. It runs through the West Midlands, which is the second largest city, Birmingham, in the UK. It's an elevated section of the motorway that runs through, and there was a need for repair of a 2-mile section of this viaduct, which was chloride contaminated because of the icing salts. This consisted of some 165 sections. Each section is just between the two columns, as you can see here. So this is one section, this is another section, another 165 continuous sections. They're separated by expansion joints, and the expansion joints were sitting right on top of the cross beams and the columns. So the salt was sipping right down on top of the cross beams and down the columns, contaminating it and causing corrosion. So Highways England carried out a repair of these. And as it turned out, there was a need to do over 12,000 substantial repairs over this stretch of motorway. The way that they dealt with it was the substructure, which is holding up the road on the top, the slab, which included the columns and the cross beams, were cathodically protected using an ICCP system, whereas the deck was protected by using galvanic anodes. Again, you have the expansion joint, and this is where the corrosion would have been happening because the water was seeping down. So all these needed to be repaired. Once again, you're going to have new construction, new concrete being cast against the older concrete, which would probably contain some chloride still, and therefore you're in need of protecting this edge, and a line of anodes were placed at 450mm spacing. There were also other patch areas that needed to be repaired as well, and as the suggestion, the anodes would go all around the edge of the repair to protect surrounding concrete. This is what the repaired expansion joint looks like. 450mm spacing, as I already mentioned. So this was a really big job, and it was going on for around 2 years. It made a lot of people uncomfortable and angry because they had to drive through this repaired sections. But eventually it was completed, and probably less than a year ago when the job was completed. So it's quite a recent job. Okay, I talked about the CC type anodes briefly. They're just the same chemistry. Basically, you have an encasing mortar with lithium hydroxide, and you have a zinc ore, and these are put into drill holes on a concrete slab. Again, this is a parking garage, and you can actually connect all the anodes, or a lot of anodes, I think up to 20 anodes in a chain, once you inserted them into the concrete. This is normally as a grid formation, so you get current distribution, a lot better current distribution than if you've got a single line of anodes as you might have in a patch repair. And this is called corrosion control. We call it corrosion control because you're trying to extend the surface life of your structure. So you are reducing the rate of corrosion significantly. You may not be stopping it totally, but you're extending the surface life by 20 years or whatever your design might be. Another example is a pre-stressed concrete box girder. In this case, it's just 2 lines of anodes that were embedded to protect the central region of that. One advantage of using galvanic anodes in pre-stressed steel or post-tensioned is that you without having to worry about it, you're ensuring that your steel doesn't get down to potentials where hydrogen evolution would occur, because the natural potential of the zinc is such that it doesn't do that. So you get safe protection. Okay, that's the after effect, if you like. That's what it looks like. And I'm just going to talk about one other system. We call it distributed anode system. All it is basically, it's just long galvanic anodes distributed in a sense that you are distributing the current better, because you can line up your anodes against the steel reinforcement. In this particular case was for an abutment that was had steel added to it, and it was thickened to take up to increase its strength. But of course, you still have your old steel, which is embedded in suspicious concrete. Some of that needed to be repaired anyway. So you need to be protecting your existing steel. So the anodes are placed in such a way to protect that. This is an example of that. You can see that the anodes are extremely long. You can have just a whole line of anodes. And it's easy to do because you're going to cover that with concrete. There's no need for drilling or anything like that. And that's what it will look like eventually. Okay, I promised a table before, and this is a whole list of the structures that we have been monitoring, and we've been monitoring long enough, beyond 10 years, so that we could determine what we call the aging factor, or the half-life of each anode. This is the one that I was talking about. It's about 7 years. On the same structure, we had embedded at the same time another area which we've been monitoring, but with a spacing of 750, and you can see that increase in spacing sacrificed the actual half-life. Although the initial current was double, what it suffered from was that it's been diminishing. The diminishing trend was much harsher. But with all the other ones, we have a constant spacing of 300 millimeters, and we could see that with the ×2 and the ×4, we get half-lives of 13, 10. The highest we found is about almost 14 years. So we've now got a whole range of anodes that we've been monitoring, and they're not far between. The ×2 anodes, the XP2s and the CC2s, have got a very similar half-life, and so have the XP4s. We think that that's actually going to improve now that we've changed the chemistry a little bit. We know that increased porosity would enhance the half-life as well, because it slow down the slowing process, if you like. So how can we then use this information? It's very, very useful information. So there's two parameters. There's an initial current that we know that our anodes can deliver, and there's the half-life, or the aging factor. So I'll give an example of how we've been traditionally designing. The set of tables that we provide, and if we're looking for a less than 0.8% chloride, and we want to achieve corrosion control, but we're using XP2 anodes, or the equivalent CC2s. Our table tells us that for a steel density of, I've taken it as 0.61, we need a spacing of 400 millimeters, or 16 inches. Okay, so let's work that out. Now that we know our half-life, which we assume to be 13 years, we know what our initial current will be and that would be representative of a climate like the UK, where your average temperature in the year is around 9 to 10 degrees. If that was 15 degrees higher, this is another thing that we worked out, and I forgot to mention, is that for every 15 degree Celsius increase in temperature, you get a doubling of the current, or halving if you're going the other way. So if our temperature is it's a mean of 20 degrees instead of 10, that will be 500 milliamps. The same anode will produce 500 microns. But on this occasion, I'm assuming 250 because it's UK conditions. The spacing we got from the data sheet, it's 400. Steel density is 0.61. We can then work out the current density that we are producing, which is 2.6 for the steel. And that diminishes, half-life tells us that diminishes with time, and we end up at 30 years Jumped a little bit there. 30 years, 0.53 milliamps per meter squared. And that's this top blue line. That's the current distribution as it diminishes with time. We also have a graph here for zinc consumption. So for 30 years, we've consumed almost 50 grams of zinc, or we will be. And the type of anode that we've chosen has significantly more than that amount of zinc. So we're okay on that front as well. But now let's turn the tables around and let's say, well, we got the details. What we need to do is we want to design a current density at 30 years. So we need to know what the current density will be at 30 years. We still want a current density of 0.4, which is cathodic prevention level, and I'm confident that if your chloride level at the beginning is less than 0.85, by the fact that you are producing current throughout the 30 years and you're increasing the alkalinity around the steel, and you're reducing the chloride because you're repelling it away, I'm happy that 0.4 will be an adequate current density. So working that out in our spreadsheet, we get a spacing of 460 millimeters, which is a little bit better, if you like. If you want to save anodes, save a number of anodes, it's less anodes for your structure. And this is the current distribution that's worked out from there. But what it does, it gives you more confidence that, I mean, initially this was not guesswork, but you couldn't really predict what would happen in the future. We now know, so we'll work from the future backwards. We'll design what our current density should be at 30 years, or 20 years, or 10 years, or however long you require your anode to be running, and work backwards to state what your initial current should be. Just showing that graphically, basically the same thing. This is the first case where we working the spacing from the tables, 400 millimeter spacing, 16 inches, for a less than 0.8% chloride concentration, steel density 0.61. Our current density will be 2.6, and we can follow the trend using our half-life concept of 13 years, and this will be the current as it drops with time. But we still have significant current after 30 years. If, however, we use a different anode, which has a different aging term, and I know that halide anodes, for example, have a much lower aging factor, aging half-life of less than 3 years. If you start with the same current density, you will see that very quickly that current is going to drop to levels that are not really usable anymore. So you need to reverse that process, really. You have to start from your 30 year and assume that this is the current that I want, and I've got to work out backwards. So you set up your 30-year current with the alkali-activated at 13-year half-life. You come back to 2 or so milliamps as your starting current, but with an anode with a much reduced half-life, you've got to start at a current density of over 10,000 milliamps per meter squared, which is, in this case, it's an impossibility. Okay, so I'll summarize all of that. What I said basically is that galvanic anodes are ideal for mitigating incipient anode formation, and I've given examples of that. That's in patch repairs or anywhere where you have new concrete cast against old concrete, and steel reinforcement needs protection, or it needs to be able to prevent corrosion from occurring. There's also other anodes that have been developed, also alkali-activated embedded anodes that can cover a range of applications in what we call corrosion control, and that it could be a grid formation of anodes that protects a certain area of your reinforced concrete. Analysis of up to 20 years of our results that we've been monitoring have allowed us to determine the aging behavior of the alkali-activated anodes, and we can now talk about a half-life or an aging term, where we know we can predict what the current density of our design will be in the future. That makes life a lot simpler, a lot easier, and gives you a lot more confidence. And furthermore, we could the understanding of the long-term behavior allows us better designs. It takes control of our design parameters and gives us an opportunity to design a lot better our actual galvanic anode system. And I think I'm stopping there. Thank you very much for your attention.
Thank you. Thank you, George.
Okay.
That was an excellent presentation. We had lots of interaction and questions that came in through the chat. I won't obviously probably be able to go through them all, but I'll just ask you a few here that I think were good questions and that were commonly asked. I think there was a question that was interesting about you touched on it briefly, but about the generation of hydroxyl layer at the steel reinforcing.
Yeah.
And the idea that you could have some type of residual protection that's built up over time. And you also mentioned how the chloride may be affected by that as well. So could you just talk about that briefly?
Yeah, sure. I showed briefly the reaction that takes place at the cathode. That's actually a very important reaction for us. It consumes oxygen and water and produces hydroxyl ions in the process of delivering electrons to the anodic side. And of course, that production of hydroxyl ions can increase your alkalinity around the steel reinforcement. We know that steel is protected by hydroxyl ions and it's corroded by the chloride ions. So, but you need a balance. You need a certain critical level of chloride to hydroxyl ratio before your corrosion can initiate. So if anything that reduces that chloride to hydroxyl ratio is of benefit. And what you're doing when you're applying a current is actually doing both things. You're increasing the hydroxyl ions and you're decreasing the chloride ions because they're negatively charged. They're being repelled away from the steel, which is also negatively charged. You're firing electrons to it, so it repels the chloride ions. And the net effect is that you're reducing your chloride to hydroxyl ratio, and therefore you're moving away from the risky area or where corrosion can initiate. And over a length of time, I've talked about 30 years there, and why I was happy with a 0.4 milliamp per meter squared current density at that stage. I'm pretty sure that you won't need any more protection of your steel. You just need to prevent any corrosion occurring, and that's corrosion current density, which is equivalent to that.
Okay. We had a few questions about new construction, and I guess that's with the last comment that you made also would have an impact on protecting new structures and newly constructed structures that may be, for example, along coastal areas that are going to be contaminated in the future. Any thoughts about new construction? Yeah,
it's pretty much what I've just said, but you start from a very good point. You start from a point where there's no chloride there. So what you're doing, quite apart from the fact that you're increasing your alkalinity gradually, you're also stopping the chlorides from getting to the steel reinforcement, or you're making it more difficult for them because they're negatively charged. So you're creating a kind of a barrier around the steel reinforcement that stops the chloride or reduces their ability to attack the steel. So just by that, you're extending the surface life of your anode. And even if your anode life is exceeded and there's no more current coming out of it, the fact that you've kept the chlorides away for a long time means that you still have that period of time before the chlorides can then diffuse and get to the steel. So you have additional life, if you like, of your structure, even though your anodes have run out. So you may be talking about 40, 50 years.
Yeah, I know that we've probably seen more commonly when galvanic anodes are used in new construction, that they're used in a targeted manner. So they may be placed under areas that the engineer knows that is susceptible in the future, around joints or beam ends and that type of thing. So you can kind of proactively target those areas up front. Also had a couple questions on partial depth versus full depth repair. And when would you use anodes around the perimeter versus on a grid pattern through the repair area?
Okay, yeah, I think I mean it's almost answers itself really. When you're not removing the contaminated chloride around the steel, and the steel concrete attached to the back of the steel, that concrete is likely to be at least partly contaminated as well. So in that case, you need to be protecting the steel within the patch as well. So it's wise to have not just at the periphery of the patch repair to protect the outside concrete, but you also got the old concrete which is still attached to the steel within the patch. So you need some anodes within the patch itself.
Right. That's assuming you have chloride contaminated concrete in the section below, or we've also seen structures which had admixed chloride from new construction, which are an appropriate application for anodes on a grid through the repair, on a partial depth repair. Another question was related to the use of the high pH as an activator for the covering around the anode. Is that causing any issues to the concrete itself, or in particular related to alkali silica reactivity?
Okay, I did actually, I've written it down, but I've not mentioned it, that one of the main reasons we use lithium hydroxide instead of any of the other alkalis is because lithium ions are actually inhibit alkali-silica reaction. So irrespective of whether you're producing more alkali, the fact that you've got lithium ions there stops alkali-silica reaction anyway.
Yeah. Just a final question for you here, and maybe you can comment on the idea that what is the relationship between the mass of zinc and the level of protection, and how does surface area come into play of the zinc? Okay.
I think I said quite a few times throughout that the current output of an anode is directly related to the surface area of the anode. So when you design for a particular current density, it's the surface area of the anode that you take into consideration. The volume or mass would just give you the life of your anode beyond, it's consumed with time. It's only consumed on the surface. Your surface area will be reducing gradually, so your current output will be reducing gradually. But if you've got a very thin layer of zinc and you have a very, very large surface area in relation to your volume or your mass, you'll very quickly consume that, so you run out of zinc. So you need to have a balance of sufficient volume or sufficient mass of your zinc in relation to your surface area, so that you can have enough zinc to last the surface life that you're designing for.
Excellent, thank you. So, and thank you, George, for joining us for Webinar Wednesday and for sharing your professional expertise with everyone today. And we really appreciate that on behalf of Concrete Preservation Alliance and all of our attendees. We thank you very much. Unfortunately, we had a lot of questions. Unfortunately, we weren't able to answer them all. So I wanted to make sure that all the attendees have your contact information. There's your phone number and an email address. If there's other questions that they want to that were unanswered, to contact Dr. Sargi direct. There is his contact information. And we have had a couple of questions about getting copies of the slides. As I mentioned earlier, those will be put onto the WeSaveStructures.info website under the events page in the next day or so. And just a reminder for future events, as I mentioned, October 14th, we're going to be talking about severely corroded structures and galvanic encasements. In November, we're going to be talking more about marine structures and concrete pile protection with galvanic jacketing systems. So once again, visit WeSaveStructures.info, go to the events page where you can not only find a copy of today's slides, there will be a video posted out there of our recording from today's presentation. So you could be able to access that in the future as well, and as well as register for upcoming events. So with that being said, thank you to all the attendees for taking the time out of your day to attend, and for many of you logging in at an inconvenient hour. Just wanted to say, in today's interesting times, I'd like for everyone to be safe out there so that together we can go save some structures. Thank you very much.